Hello. We are back. So today I'm going to do some actual self-studying, and the plan is to do something on measure theory. And I have done measure theory before, but it's a long time ago. I kind of need a refresher. And the reason I want to do this is that I want to do some probability, kind of like the actual rigorous way, which I've never really dived too deeply into, and I think I want that as part of my interest in data science, statistics, and so on. Alright, so what I have done, I have found some notes on the internet by somebody named what was the name? Let me just double check. Spry was the name. Okay, I got that totally wrong. Right, so I try to follow those notes, and I probably won't be following them. I won't be doing everything, and I might be a little loosey-goosey somewhere. If you want somebody who does this really rigorously and just does all the nitty-gritty details, and also the reason for all of this, you should check out Math with Ming. He's got a series on measure theory, which is going much more into why we need this at all. Right? But it's needed for probability, and that's kind of our motivation for doing this. All right, so let's start from somewhere. So first of all, these note sets, they define an algebra. And algebra is one of these super overloaded words. It's a super overloaded word, and it means different things to different people. I think the most common use is some kind of vector space with some external product, or whatever you wanna call it. And this is not it at all here, right? So this is used in a different way. So an algebra, the definition we'll use here is that we have S, which is a non-empty set. A non-empty set. And then the idea is we have a collection of subsets of S, right? So the way I prefer to write this is that we have this collection. It's denoted by a large sigma. And what it is a subset of the power set of S. And the power set, just to make sure, the power set is the set of all subsets. So it's a collection of subsets, and this collection, we call that algebra, and if it satisfies the following conditions. So first of all, the entire set itself should be an element in this subset. We should have that if some subset of S is in sigma, big sigma, that means that the complement is also in sigma. And again, there's different way to write complements. This set of notes uses this small c superscript, so I'll use that. Right, and finally, if we have two sets, E and F, that are in sigma, then that should imply that the union is also in sigma. Oh, and sorry. So this is, I forgot something. So this is an algebra, so we're not in sigma algebra land yet. So you just add a zero subscript. Right. Yes, and the reason for this has to do with the third condition. We'll get back to that in a moment. Okay, So, of course, it's a very abstract definition. I don't know if I'll spend some time on why this is necessary for probability. If you've never seen this before, it seems like it comes out of nowhere. But let's prove a few not probabilities, a few properties. Okay, so let's call it a proposition. So if we have S with the collection of subsets, an algebra, then there's some stuff that will hold true, right? We'll have that. Well, first of all, so let me write them out. Probably easier this way. So a proposition here is that the empty set. Oh, once again, it needs to be a sigma 0. If the empty set is a part of sigma 0. Oh well, sorry. That's what we want to prove. We will also have. Let's see. Well, let's see. We'll also have that if E and F is in are subsets in sigma 0, then we'll have that not only is there union in sigma 0, the intersection will be as well. Right. And then for the third one, we can generalize that. Right. So this is just a binary operation in the axiom or in the definition, but we can easily extend that to a finite set. So that means that the union of all of these will be in sigma 0, and similarly the exact same thing will apply. This will also imply that the intersection of all of these is in sigma 0. Okay. So let's go over the proof. Should be pretty rudimentary, I hope. So since because of the I hope it's not too confusing that these numerals are used both in the proposition and definition. In this proof, I'll always refer to the definition here, right? So, by the first axiom in the definition, we'll have that the entire set is in sigma 0. But then, by the second axiom, we have that complements should be in sigma 0. So we'll have that the complement of S, and that is nothing but S minus S, right? That's how we do a complement. We take the universal set, in this case S, and we subtract the relevant set, and in this case that is also S, and this is of course simply the empty set, where we know that this must be in sigma 0. Right. For the second property, all right, so this is the first one. Yeah, sorry for the confusing use of enumeration. Okay. Also here we have, for the second one, we assume that E and F, That's not good. Assume that E and F are in sigma 0. Then we know by the second axiom, we know that means that the complements of these two sets are also in sigma 0. And then by the third axiom here, we also have that the union of sets is in sigma 0. So we use that on the complement we just got. So that means by the third axiom, we have that the complement union complement of C union complement of F, that must be in sigma 0. But this, using the Morgan's laws, this is simply the same as E intersect F. So maybe we can draw a picture here. So this is all of S. Inside here we have E and we have F. So let's see. So we see, so the complement of E, this is all of this, and the complement of F. I've made a mistake, so it's good I draw this. I drew this. It's like this. Right, so you can see what's actually left now in here. So this is just that's the thing. This is actually the complement of E intersect F, right? But then again, we can use the second axiom again to say the complement of that set will be in sigma 0, and of course the complement of the complement is simply the set itself, right? All right. Just checking if you're awake. Can I even see chat? That's actually a really good question. Good question. Well, I wonder if there's anybody in the actual chat. Okay, that's kind of just a minute. Let me see if there's actually any people in chat. I see no people in chat, so well, all right. That's fair. I'm a new streamer. All right, and then 3 and 4, I won't go too much into those. They basically just follow by induction, right? We can do the binary case where both unions and intersections are preserved, and then you can simply, it's no problem to just extend that to a finite number of unions or intersections, right? So let's just write that. Follows by induction. All right. Okay. So those are some basic properties. Can you even hear me now? I think what I'll do. Yeah. I don't know if the sound was gone. I hope not. But all right. Let me continue. Okay, so far we've dealt with an algebra, what is called an algebra, at least in these notes. We want to extend to what is called a sigma algebra. And in general, adding this sigma, right, so this is, that's how I pronounce this funny looking O. And in general, that means we want to extend something from a finite collection to a countable collection. And in particular, the difference here is that a sigma algebra is an algebra. Yeah, let me just... So we have an algebra S, and this time I dropped the zero subscript. But so the idea here is, right, that it still needs to satisfy the two first. Let me just see. Can I actually do this? I'm trying to copy. Oh, that's oh, I'm bad at this. Really bad at this. I think I did the same thing in the last stream as well. I wanted to select that. Okay, guess. Well, you know what? Let me just. So it's an algebra, so it still has to. Let's just write out those. It still has to satisfy, right, that S, the entire set is in sigma, and also, so this is a large sigma, right? So the sigma in the definition, the name, that's the small sigma, and the collection of subsets is the big sigma. Yeah, mathematicians love to use funky green letters. I apologize, you get used to them. We also still have that if E is in sigma, then the complement should be in sigma as well. And then the important bit, right? So remember that for the algebra, the ordinary algebra, we have that if we have two sets from sigma, then the union would be in sigma as well, and that means we can do it finitely many times. But here we assume that we can actually do it. We can extend this to a countable set, right? So if we have that for all, we have a countable collection here. Yes, I hope you. This if you haven't seen this upside down A, just means read it as for every. So for every natural number, we associate a set in sigma. If this is the case, then it should hold that the infinite union should again be in sigma. Right. Yeah. So very much like, of course, the proposition we already proved up here, that's of course still correct. And for a sigma algebra, you can extend 3 and 4 to oh my god, did I write an infinity down here? That was definitely not supposed to be the case. This should of course only be a finite. For the algebra, sigma 0, it's only finite. For the sigma algebra, you can actually extend it. All right. Let's see. So there's some nomenclature. Is that the name? There's some names associated, some fancy words. Maybe not so fancy. So we call elements in in sigma. We call them you know what? Let's exponent sigma are called measurable and like the tuple of S sigma is called a measurable space. Alright, and I guess this is as good a time as any to know that, again, why are we doing all of this? Because if you've never seen this before, this is just abstract nonsense, right? But the idea is that in probability, something is measurable. That means that we can associate a probability to it. And the whole problem of this is a lot of the time we'll deal with subsets of R, right, of the real numbers or the natural numbers. But especially for the real numbers, it turns out that intuitively one should think that we can associate a probability or a measure for any subset of the real numbers. And it turns out we can, because there are actually some pretty nasty subsets, and that's kind of why we develop measure theory in the first place, right? Is to deal with this. All right. So that's kind of an aside. Hopefully some motivation. If you've never seen this before, probably go watch Ming's streams. I think, because I'm just jumping into the deep end. This is mostly a self-study. Yes. All right. So a very important construction we can do. So that is if we are given a set. Given a set S and a collection of subsets. Collection of subsets. Oops. We call this C. Fancy letter C, but that's neither here nor there. So in general, this collection of subsets, it will not be a measurable space, right? Is not a measurable space. There's no guarantee that C might not be S sigma algebra. And of course, generally it will not be. Did I say sigmoid algebra? It's called a sigma algebra. I've been doing machine learning for too long, where you have sigmoid functions all the time. It's a sigma algebra. But what we can do, we can instead define the smallest. So we take sigma of C, and again it's little like sigma as, I guess you can view it as a function, right? But we use the letter lowercase sigma a lot. But the idea is that sigma of this collection of subsets is the smallest sigma algebra on S that contains the collection C. And in practice, how do we do this? What we do is we take an intersection over all sigma algebras where the collection C is a subset of. Maybe I wrote that backwards, but that's kind of the idea, right? So in general, there will be like there can be like any number of infinite number of sigma algebras on S that contains C. But if the idea is that if you take the And here I am, of course, I did not mean the union. I do, of course, mean the intersection. Sorry. Okay, so what we kind of need to do is we need to. That's the question is this really a sigma algebra? Yeah, and we'll have to. We're going to have to prove this. So yes, it is. And we need the proof. Oops. If you can read that, is that even possible to read? I tried to write it a little nicer. Just checking if there's any chatters. There's not. That's fine. Hope to see you someday. No, so what we need to do is, right, we need to prove that this is indeed a sigma algebra. And that does, let me just, so we have a notation, right. So we need to show that the three axioms are satisfied, right. So first of all, we need to prove that S, the set itself, is in this this intersection, and we know since S is a member of any sigma algebra. Let me. Should I give this an index, or I don't know? Since S is an element of any sigma algebra, it will also be in the intersection. In an arbitrary intersection in there, even. Oops. Sorry. Oops. I'm not good at this. There it is. An arbitrary intersection. So that means that S is indeed an element of this new sigma algebra, or this new set. We don't know it's a sigma algebra yet. And I mean, in kind of the other two are similar, right? Let's assume that. No, sorry. This is of course the. Assume we have a general element, or let E be a general element. It is our set, right? So if E is in the set in the intersection, then E must be in every sigma. But because every sigma is a sigma algebra, we must also have that the complement, therefore the complement is also in every sigma algebra, and hence it is also in the intersection, right? Okay, and finally, I mean, it's kind of the same argument. If we have like a family E, where it's a countable family of sets that are in our set, sigma of C, that means then, that means that every EI is in every of the sigma algebras we take the intersection over. And since there are, so that means that since all of these sigmas are sigma algebras, that means that the infinite union, the countable union, must also be in sigma, in all the sigmas, and again, since it's in all the sigmas, that means that this must also be in the intersection of all the sigma algebras. Right. QED. Okay, so in general, this is going to be a rather useful idea, right? That we have some kind of subset, a collection of subsets of a set, and from there we kind of construct a sigma algebra. And of course, and again, this is going pretty fast, so if you've never seen this before, I apologize. But the idea is that the most important one that we're going to look at is called what is called Borel algebras. Okay. So in general, well, actually, we could do it in a general topological space. Oops. Or even a metric space, or if that doesn't mean anything to you, just assume we're talking about the real numbers, because that's going to be the important case. But we'll be super interested in the what is called the Borel algebra of let me just. This is how you usually write a topological space, right? So X is the underlying set, and this tau is like a collection of subsets, and this collection are the open sets. If you're just in a metric space, you can or Euclidean space is just the usual definition, right? That every point is an inner point of the set. But the idea is that we should just call tau all the open sets. This is called the Borel algebra. Yeah, sorry, yeah, that's not what I meant to write. What I meant to write is that the Borel algebra of this space is a sigma algebra generated by the open sets. This is the Borel algebra. And as I said, the main example is the Borel algebra on the real numbers with the usual topology. And in fact, this is so this is so common that often we'll just, if we just write a B, it'll be the Borel algebra on the open sets. Yep. Yep. All right. So what we get here is a Borel algebra, right? For the reals, we get all the open intervals, of course. We get all the complements, so that means all the closed sets are also there, and we can do countable intersection and countable unions. So that means we get quite a lot of sets, right? But the problem is that it turns out that we do not get all the subsets. So that's kind of the reason we do all this, right? Is the Borel algebra on the reals, is that equal to the power set on the reals? No, it is not. So sad tears, unfortunately. And this, it turns out that actually the subsets that are not in, they will all be kind of nasty, or they're non-constructive, right? You actually need the axiom of choice to construct them, but most of them are in fact not measurable. But any set you can think of, or any set you can basically write down in a constructive way, will be measurable. Yeah. And again, measurable means it's part of this algebra. And again, if people calls a subset measurable without any qualifications, right, without specifying a sigma algebra, it'll be with respect to the Borel algebra. All right, let's see. On the note, there's a proposition. Let's see. And it says that if we, let's define the set I, that's a fancy I, but we let it be the set of intervals from negative infinity to x, so they're closed intervals, where x run over all r's, right? Then the smallest sigma algebra containing all these intervals is actually the Borel algebra. So this is kind of a way to characterize the Borel algebra that might be easier to work with in certain situations. Okay, so we need a proof of that, of course, and we want to do two ways, or two comparisons, you might say. So we want to show inclusion one way and inclusion the other way, right? If one is a subset of the other is a subset of the one, I guess, then they must be the same set. All right. So let's see. So let's start by doing this way, right? So let's see. So we want to show that. We want to take an element in the. Oh, that wasn't. I wrote it like this. No, that still looks like something else. Let's see. It should be an I, right? The fancy I. And that means so we have a set of this form, an interval. So the question is, can we show that this is in the Borel algebra in other ways? Can we construct it by an accountable union or intersection, right? So we know can we show using like the definition and or theorems about what we know must be in a sigma algebra? Can we show that this interval is in fact in the Borel algebra? Okay, so how can we do this? Well, turns out we can do an countable intersection. Alright. So we take a countable intersection. Take it like this. So we need an open interval, or just an open set, but intervals will typically be, it's kind of what the building blocks of open sets in the reals. But what we can do is we can kind of say, okay, so we kind of want to turn an open endpoint x into a closed endpoint x. So what can we do? Well, we can take the x and then add a little an epsilon you can think of, if you kind of like. So you can see here, since we this is a countable intersection, right? But we can see for any number that's bigger than x, at some point the 1 over n will get so small that that number will not be in this intersection, but x will always be in this set, right? So in the end, that means that this is actually equal. It's actually equal to. It's actually equal to this, right? So that means that we have shown that this is in fact a Borel set, right? So so that's actually it. Then there's the other way, which probably a little harder, right? So so let's see, what do we have? So given a Borel set, let's see, what do we do here? Yeah, we need a few. I'm looking at the proof here. I'm trying to go. So let's do an observation, right? That we know that. Boom, boom, boom. Yeah. So let's. Yeah. What is the smartest way to go about this? So first of all, there's kind of like a note here that if we so in general, elements of sigma of I, we can say something about the question is, are they open? Do we have some open sets in there? What is the one? I think it's a better way to do this. Let's just say this is like a, oops. Let's kind of say like this is like a, oops. Jesus. This is kind of like a lemma. So we want to show that the intervals, the open intervals, from minus infinity to a. Sorry, they use here they do in fact use an x, just like they do in the definition. But we want to show that this is actually, such sets are elements in the sigma algebra generated by I. And how can we do that? Well, we can, because we're looking for a sigma algebra which contains all of these sets. Well, we must have that, at least, we must have that, for instance, a countable number of unions of elements in big I. Those must also be in the sigma algebra generated by I. And what we can do here is that we can kind of do a similar trick. Right, so what we're doing is we are starting from negative infinity, but then we're going up to x. But remember, we need this for this to be a closed interval, right? Because that's what we're working with in big I. So where did that come from? Okay, so what we can do here instead, let's subtract 1 over n, like a small number that gets arbitrarily small as we do the countable union. So that means whereas previously in the first inclusion we were kind of like approaching the x from above in a sense, and here we are kind of approaching the x from below. But similarly, it's kind of with each union we kind of add more until we don't quite get to x, right? That's the point. No matter how big n is, we will never get quite to x. We'll always be a little bit before. We can get arbitrarily close. So in other words, what we actually get here is an open interval. Okay. So in other ways, that means that, well, this is the proof of this. These will in fact be in sigma of I, right? the smallest sigma algebra containing these intervals up here, it must also contain the associated open intervals. Okay. So let's see. And from that we can see that you can kind of a corollary within this. From this we can from this we can also see that like a finite interval, open interval, right? That will also be in this smallest sigma algebra. And why is that? Well, what we can do is, since the sigma algebra is closed under. Oh, I don't think we showed that. Sigma algebra is actually also closed under set differences. Oh man, I forgot that. But anyway, that's maybe I should just postpone. Oh, that's left as an exercise for you. It's left as an exercise, I guess. So the idea is that if we have an E, if you have an E and an F in a sigma algebra, that means that's E minus F is also in the sigma algebra. Right. So we use that, which I forgot to prove. I'm so sorry. But what we can do is that we can, if we take negative infinity here, so this one, how do we do this? Okay. And here we should of course have that A is less than B. But what we can do is we can take, we know that this, we've just proven that this set is in the smallest sigma algebra, and if we take the set difference with this set, and that's why I take the closed one, that's also in the sigma algebra. That's where we started basically. So this must also be in the sigma algebra, so we have that this must, so the idea is of course that what is this? This is simply the interval from A to B, and this must then be in the sigma algebra, and at this point the sigma algebra we're looking for is called this. Okay, so now what we kind of concluded a lot about which sets are actually in this smallest sigma algebra. But we want to show let's see. So what were we actually doing? So we want to let the we want an arbitrary open set. So the open subset of the reals is open, and that means that it's open. That means that for every x in G, that means there must be a small number epsilon, so that maybe it's easy better to draw this, right? We have the set. I'm drawing it in 2 dimensions because it's easier to show, right? But the idea is that this is the open set, and we have our x, and then there must be like a small ball around it here, right? That's an open ball. It must be totally included within G, right? That's the definition of a set being open. So the idea here is that, well, because now we are back in 1 dimension, so the idea is there must exist. It's 1 dimension, so now it's just a little interval around x. We must have that this epsilon is a small number, right? But we kind of enclose the open interval around it, and this must be completely within G, right? So that's kind of what's happening here. This is in 2 dimensions. If I draw it in 1 dimension, it'll be like x is here, and then we have x minus epsilon here, and x plus epsilon here. But the thing is, we want at some point to get back to like a countable collections. So what we can do is here that, in fact, because we can always choose, in general, this epsilon, it's a general real number, but we can also always choose an epsilon. I'll just give this one a prime, right? Because this is not really the epsilon we want. We actually want an epsilon that is between 0 and the first epsilon we chose, but we choose it so that this epsilon is rational, right? So this is a property of the rationals. You can always find, if you have 2 reals, there's always a rational between them, right? So 0 is a real, epsilon prime is a real. That must be and so it's kind of like we can always kind of turn it into an even smaller interval such that the distance is actually rational. Okay. And I think in this proof we even call it, we even give it an index, right? Because this depends on the x, which x we are inside G. Yeah. So what do we say here? I'm trying to follow this proof. Maybe I should have. Well, this is a self-study session, so I might just have to read it here. All right. Yeah. Okay. So what is the idea? Okay. So, okay, let me go back. So the idea was that, how do we do this? Okay, so the idea is, of course, that we also want to make sure that x is only... So this is kind of, this process, right? It is kind of, it's very similar to showing that the reals are second countable, if that means anything to you. So the kind of idea that we can take any open subset of the reals, or Euclidean space in general, you can always write that as a countable union of sets, open sets coming from what is known as a basis. Okay, that's a little. Let me just check here. No. Sorry. Let me try that again. What is the best way to do this? Yeah, I think the idea here is that okay, I'm erasing way too much. Yeah, okay. The idea is let's say some real e, but what we'll be doing is that we'll actually say we want minus 2e and plus 2e. Okay, so we can start by epsilon half, and then we can kind of double if that. But we can always choose an epsilon in this way. So this is equivalent, right? So I think that is the idea here, like that. So we have. So this is like x minus 2 epsilon, and this is x plus 2 epsilons. Let's see if, oops. You can see me thinking out loud. It's not pretty. No. So that's the, okay, that's, so the idea is, and then we can also consider the interval. We can also take this interval. Okay, that's the, now I get it. Right, so that's like the big interval. We can always choose such an interval around a point in G, right? So it's inside, all inside of G. But of course, if we take this interval, it must also be inside of G. And now we use that. So choose Chaucer. Can't write either. Okay. So we choose a rational number qx that is inside this interval. We can all, once again, that's a property of the rationals, right? That thens inside the reals. So that means between two reals, like x minus e and x plus e, we can always find a rational number. All right. So we choose one such number. All right. Did I get a text? Maybe I got a text. So let's see. This interval, yes. And what do we have? Alright, and what is the idea here? So let's see. Okay, so what we should just draw the situation again, right? We have x. We have these two intervals around it. That's a x minus 2 epsilon, x minus epsilon, x plus epsilon, x plus 2 epsilon, and we've chosen an x, sorry, we've chosen a q in here, qx. And of course, I don't know if there's any of course here, but the idea is that what is the distance between x and q? So x, we've chosen within this interval, right? So the q, so we must have that x minus this q, right? It must be smaller than epsilon, right? We've chosen inside this interval, so it kind of has to be. So what does that mean? Well, that means that, so that means that if you take like if you center the interval around qx instead, right? So maybe I should use that I have colors. If now we take this interval instead. Well, the idea is that this would be qx minus epsilon. This would be qx plus epsilon. You can see this interval, it must be totally contained. It must be contained within the interval we started with, the double interval, right? So if you look at q, whoops. No, wrong color. Yeah, I'm a professional. Oops. We must have that the red interval, let's use the red color then. The red interval, so that's qx minus epsilon to qx plus epsilon. That must be entirely contained within the original interval, right? So that's the x minus 2 epsilon, x plus 2 epsilon. Okay. So what have we achieved here? Okay. I think within So the idea was, I think, that without loss of generality, we can actually assume that this epsilon is rational, right? Because we can always, if you have found a real epsilon, we can always use an epsilon that's between 0 and the real epsilon. We can also always pick a rational epsilon. So that's kind of important now, because now if we look at this, right, so we have that Q and epsilon, those are both in the rational numbers, right? So that means that this if we do this kind of trick for every x in G, right, we'll get a set of rational numbers for each, but there's only a countable number of rationals. So that means that if we do a union of all these intervals, there will in fact always be a countable union, right? So we can always write G as a countable union. So the idea is this game, we can play this game for every point inside of X, every sign X inside of G. That means we get a collection of such sets of rationals for every point in G, but it doesn't matter what cardinality G has, doesn't matter how big the set is, because we'll always get with a subset of Q squared, you can say, right? So we even if we do choose such an interval for each x in G, we'll always only have a countable set in the end. Yes, final union. Yeah. So it follows that means we must have that this G is inside the algebra here, right? I guess. Yeah. Let's see. Let's just get this right. So. So any G is open. That means it's a G from the. It's an element of the general, from the Borel subset, right? Certainly the. Let's see. So this means that yes. That means that all the open intervals are in the. Where did I even use this lemma? Oh yeah, okay. So that's what. Okay, yeah. So we now know the open sets. The open sets are in the smallest sigma algebra generated by I. Right. So if we can show that the open sets are can be written as a countable union, we should be done, right? No, okay. From this, we can conclude that, right, So the open sets means the open sets are subset of the algebra. And yeah, okay. And since this is the smallest algebra generated by I, that means it's also at least this is part of this, and since so that means yeah, since the Borel algebra is the smallest sigma algebra containing the open sets, and we know the open sets are in this smallest sigma algebra, we must have that this is equal to B. Okay, that was a very, very confused. I think I confused myself a few times here. Let me know if you want maybe a clearer proof. Of course, this is mostly for myself. I think I understand it now. Yeah. All right. I think this is the proof. Again, let me know if you want a clearer exposition of it. I guess I should also introduce the measures now that I am here. We just check if there's any chat. There's not any chat. Okay. Let's get on to measures, because of course that's what we really want to do. So these nodes, they kind of introduce the measures in like a two-step process. Right. So we're going back. We're starting with an algebra. We're going back. So it's not a sigma algebra, it's just an algebra, right? So we only have finite union and intersection. So we have we have a set, and we have a collection of subsets, sigma 0, right? This is an algebra on the set S. So we can consider mappings. Mappings that are from sigma 0 into the extended reals, and this is kind of important. So it's not just the positive reals. We actually have infinity included. Right. So we can have, and the idea of a measure is kind of, well, in the reals, what we really want to do, we want to measure the length of a set, right? So for instance, we can imagine like for instance, all of R that has a length that's infinite, right? So we want to be able to assign an infinite measure or length to certain sets, right? All right. So therefore we use the extended reals. So let's see, what are we? Okay. So we consider such mappings. So that we consider two different mappings of this kind, right? Let me just write them. So there's a mu 0, and in general we will use the Greek letter mu to sounds like a cat. Mu. We'll use that to designate such a mapping, right? So let's look at two different ones, and the domain and codomains are the same, of course. Right. So we will call. So here's a definition. So we say that mu 0 is called finitely additive. Okay, the idea here is of course that what they want to do is Sorry, we want to consider both algebra and a sigma algebra on S. And this, I'm very confused. Not used to streaming. Let's say that the sigma is an actual sigma algebra, right? And once again, there's this the distinction between an algebra and a sigma algebra is that the algebra is finitely additive, whereas the sigma algebra is countably additive. Okay, but we call, let's start with the algebra sigma 0. We call mu 0 finitely additive if mu 0 of the empty set is 0, and if we have that E and F sigma 0 disjoint, then we can simply add these measures, or wannabe measures, I guess you can say. And of course, this should be the union, right? Since they're yeah, let me just write it down and draw a picture. So the idea is, if you have E here and you have F here, so this is the area. That's kind of what the measure is. It can be an area, length, or volume. Then it makes sense that if these are disjoint, then we can just get the total area by adding the area of the individual sets. Of course, it would be a different story if they were overlapping, right? Then we can't simply add them. We will get back. That's an important. There's ways to get around this, which we'll get to later, of course. So similarly, we say that the mu, so that's the mapping on the sigma algebra. Oops. We say that it's countably additive. And what do we need there? So once again, if once again we need the measure, or proposed measure, I guess, of the empty set to be 0, and then we need that if we have a countable set of subsets, and these should of course be in the sigma algebra. If they are disjoint, then we have that we can get the measure of the union of all these sets. That will be the same as summing over the measures of each of them. Right. So it kind of takes the idea of finite additivity and then extend it to countability, to the countable case, right? And this turns out to be kind of like we really want this property, but that's also the property that turns out to make it impossible to have a measure on all of the subsets of the real. Okay. So of course the definition that we want to so we're mostly interested in the sigma algebra case, not the ordinary algebra, right? So this leads us to the following definition. So what do we say? Let S sigma be a measurable space. So again, that means that S is just a set, and sigma is a sigma algebra on S. then a finitely additive, not finitely, sorry, that should of course be the countable one. This is a map, right? And once again, it's from the sigma algebra into the extended reals. Oops. Right? Yes, it's called a measure. And that's basically the most important definition, I guess, in measure theory. But once we have defined a measure, then if we have the triple, we call the triple of the set, the sigma algebra, and this countably additive map, we call that a measure space. All right. Yes. So maybe I think I will end the stream soon because I've been speaking for a long time and I'm still getting used to this. So let me just check if anybody has written any comments. There are in fact no comments as far as I can see. All right. No, so what is, I mean, again, I hope you have seen some of this before because otherwise it's probably kind of weird. All of this, a lot of what is the goal? What is I want to get from all of this? What I want to do is study probability. So a very special kind of measure space, right? If you have a measure space, and well, it's the same definition here, but because it's another field, so we just use different letters. So we have a set. It's not called S. It's called omega. We have a sigma algebra. It's not called sigma. It's called F. And we have a measure. It's not called mu. It's called P. And of course, the idea is that P has to do with probability. But this is called a probability space. Called a probability space if I think actually all it requires is that the probability of the entire set is 1, right? So the idea is that this is omega is a set of outcomes F is a collection of what are they called in events. And finally P, of course, is probability. And hopefully this is, you might have seen something like this before when you studied probability. If you've only done like elementary probability, this F collection of events might be a little confusing, right? But once again, it comes down to this thing that just like we cannot assign a measure to every subset of the reals, we also can. There's also if the outcome space omega, if it is the reals, right? Or just an interval, for instance, if you choose a number uniformly between 0 and 1 in the interval, right? Then the set of outcomes is simply the interval from 0 to 1. But it turns out that the subsets events, right? F, remember, that's subsets of the set of outcomes. There's some of those we can't associate a measure to, or in other words, we cannot associate a probability to it. And these sets are, they're kind of crazy, right? But we simply need this convention, right? There are non-measurable events or non-measurable sets. All right, this is kind of what we are. This is the goal, right? This is what we really want to work with. All right, I think I will end this stream here. Got through a lot. I got confused a little. And again, if you want me to make a better video about that proof, I'll look into it. But thank you everybody. Not a lot of people have been watching, but that's okay. We'll get there eventually. Have a good day.